welcome to the USC Architecture Public Event Series. I'm very pleased to be able to share with you Jun Sato, our distinguished lecture this evening. I'm Milton Curry, Dean of the USC School of Architecture, and again, welcome to our Public Event Series. This lecture is made possible by the Nabih Youssef Endowment Lecture on Structural Design Innovation Fund, and we're pleased to have the support of Nabih Youssef for this lecture. I want to introduce Professor of Practice Gary Page, and Gary will lead you through the evening and introduce Professor Sato. Gary?
Thank you, Dean Curry. Welcome all to USC Architecture's Fall 2020 Virtual Lecture Series. It's my pleasure today to introduce Professor Jun Sato. The last time that I saw Professor Sato, a little over 2 years ago at the University of Tokyo, with a group of USC graduate students for a lecture that he gave with his colleague, Professor Yusuke Obuchi, on their recent and current work. It was a compelling afternoon, and I hope that he'll touch on some of the ideas that were discussed that day. For those of you that aren't so familiar with Jun Sato, if you're a student of contemporary Japanese architecture, then I'm quite certain that you're familiar with his work. Professor Sato's list of design engineering collaboration reads like a who's who of recent notable architectural engineering works in Japan. He has developed transparent, lightweight, and ductile structures with geometries of naturalness through his collaborations with architects such as Kengo Kuma, Riken Yamamoto, Toyo Ito, Su Fujimoto, Junya Ishigami, and others, and through workshops with students at Stanford University, Harvard GSD, and other institutions. Several projects where Professor Sato was the design engineer include Su Fujimoto's House N, House NA, the Tokyo Apartment, the Musashino Art University Museum and Library, and others. With Junya Ishigami, he engineered the Balloon, an architectural installation and truly remarkable feat of engineering. The Extreme Nature Project at the 2008 Venice Biennale, and more recently, he's collaborated with Ishigami on the Jin's Eyewear Shanghai store, another truly extraordinary gravity-defying work of engineering, as well as the 2019 Serpentine Pavilion. He worked with Kengo Kuma on Sunny Hills Oyama Shop, Kawatana Onsen Community Center, and the GC Prothero Museum Research Center. And there are others. The list of works and collaborations is extensive. As I see it, one of the common threads to all of these works is that they embrace the role and importance of experimentation, the title of one of the chapters in his book. Another common thread is that they're structurally innovative, even poetic, particularly in the way that the structural concept amplifies the spatial concept and becomes a defining attribute of the architecture. One thinks of another Japanese architect, Kazu Shinohara, and how works like the House in White, the Umbrella House, the Tanakawa House, and the House in Uhara explore the point of contact between the rhetoric of structural elements and the spatial poetics. Similarly, I would observe that Professor Sato is not only a problem solver, although I suspect that he relishes extreme structural problems. Case in point, another chapter in Jun's book is titled The Site. There's a full-page image of what I imagine are members of the engineering and fabrication team positioned next to and above Ishigami's 1-ton helium-filled floating mylar balloon. The image is titled Fervent Repair Work. The short caption reads, "An unexpected transformation occurs in the construction because the external forces were different at the time of floating." Yet I would also maintain that Professor Sato is not just an extreme problem solver, but also a poet engineer that contemplates questions of engineering and architecture, not only quantitatively, but also qualitatively. And of course, the other common thread is that he was the structural engineer for all of these projects. Currently, Professor Sato is an associate professor at the University of Tokyo, a visiting professor at Stanford University, and chief executive engineer at Jun Sato Structural Engineer. After the lecture, we'll be taking some questions. Professor Takako Tajima and I will be co-moderating. And again, I want to echo and acknowledge the support of Nabih Youssef for his ongoing commitment to the USC Endowed Lectures on Structural Design Innovation. I cannot think of a person more befitting to deliver this lecture than this evening's guest. Please join me in welcoming Professor Jun Sato to USC.
All right, thank you so much, Gary and Milton, to introduce me. This is my pleasure to join this lecture series. Thank you so much for inviting me to this exciting lecture series. This time, I will talk online, but have tried to visit your school or USC in February, but it had to be postponed. I will try soon, very soon, to try the workshop in USC, hopefully. Can we start? I'll start my lecture sharing the screen. Right, shall we start? Right. This time, I'll talk about what I am focusing in these years. It takes around 5 hours to talk all of them, but I will try this time to make it 50 minutes. So some of them are really short. I'll show you as many keywords as possible. And in these years, I'm focusing to transparent structures that can provide komorebi naturalness. I have interest in composing structures with thin or transparent, translucent elements. And these structures have potential, I could find these structures have potential to serve as environmental filters to create komorebi space. Komorebi is Japanese word. We have some terms indicating natural and comfortable space. Komorebi is the one, sunlight through leaves in the woods, like this. And Sazanami, the ocean ripple, or containing sound. Seseragi is more complicated, but basically river stream. It is containing sound and atmosphere, such as humidity or smell, or some moss will be grown up on the stones, or cool air or breeze around. I have started to analyze these scene or site with two-dimensional or spectrum analysis. So that means that a light condition, optic condition can be analyzed. So structural performance and optic condition will be optimized. So multi-objective optimization can be done for the structural design. To realize these structural design, dynamical operations should be performed, of course, and we should manipulate the geometry as well. And I'm running 4 or 5 workshops a year to show the method of realizing those structural design as an experiment. So, finally, the structural, those structural design will show something morphogenetic forms based on geometry, materials, dynamics, craftsmanship, or site boundaries. The technique to realize these structural design, we need a technique of omission. The engineering is a technique of omission. We always don't have enough time. We don't have enough money. So we have to think in that condition, under that condition, how to make it feasible. So we have to omit. We cannot check every phenomena. So we have to select which phenomena or which formula to be checked. And we can find it is possible to build or not. Right. At first, the dynamical operations I will show. And one of the most simple way of using structural performance is like this. This is Park Group Fiversberg in Netherlands with the Junya Ishigami. The structure is composed of curved glass wall, and vertical element of the structure is only these glass sheets. And because the plan is like this, something is synapse-like triangle or shape, and it has curved wall. Or well, we can give the curvature to the thin wall, and these thin walls can resist gravity and wind load as well. And when the thin wall could be curved like this, this is showing the relationship between radius and buckling strength. The radius, when radius comes small, or the buckling strength comes almost twice bigger, or sometimes 4 times, 6 times bigger. And so, depends on the load distribution, we can give the curvature to the stressful area. And for this project, I have optimized the location of beams as well, or the spacing of the beams. That means pattern of beams could be optimized to distribute the load to load evenly to the or to the stressless area on the glass wall. And finally, we could build this structure with only 10 millimeter plus 10 millimeter double layered glass. You can see the construction site on the left photo. The white lines you can see, those are beams assembled in an optimized way. When discussing with Junya Ishigami, we try brainstorming again and again, and it takes really a long time. 5 hours is rather short, 5 to 8 hours on each day. And we discussed a lot. He asked me a lot about the structural or phenomenon. And I have to explain how the buckling phenomenon happens, how to control the buckling strength, or some materials, how to manipulate. And through those detailed thinking of each phenomenon, sometimes a new structural or design idea comes up. So these discussion is necessary. But this is unique for Jun Ishigami. Not all the architects, with other architects, I don't discuss so long. And there are some simple way of embedding structural design into simple geometry. But I'll skip these at first, and I'll talk about it if I could have time later. For example, this is simple single-story building of the clinic, veterinary clinic, and the structure is composed with 6mm plate shelves structure made of 6mm steel plate without backboard. You can see the transparent shelves because of non-backboard. These are the construction sites. And we have to control the three-dimensional buckling phenomena. And this is which Gary introduced. This is a project with So Fujimoto, the museum and library in Musashino University. And for this library, I have embedded the thin ramming structure. Ramming is a German term. I think it is called rigid frame or frame structure. And it could be thin and thin like this, and embedded between these bookshelves. And to control, to make it feasible, we had using the thin columns, we have to take care of lateral buckling here, lateral buckling. And some others, but this is the ramen structure is very simple structure, and this building has really simple view, but using the some structural manipulating some structural performances, the unique structural design can be created based on those performances. The structure itself will be concealed, but it is working to create the space. So I think this can be recognized as one of the way of structural design. And I like this house. I cannot talk about it so much, but a house in Kurua Coast. It's a timber structural house. And it has a simple shape like this. And inside there, there's a perforated steel sheet working as bracing here on the first floor. And that shear wall is stabilizing the columns located around here. And the columns are cantilevered up to second floor. And finally, because these columns can work against seismic or wind load, we don't have to put shear wall on the second floor. This is also a simple way of using structural performance, but we can, I think you can see how the structural design can be embedded into a simple geometry. And I think some of you have interest in optimization, form optimization. I'm trying the manual form optimization and a little automated optimization. One of the project could be done in this community center in Kawatanaonsen with Kengokuma. It has polyhedral form, like something like mountains, like this, and it is made of steel tube structure and covered with concrete surface. And for this structure, I have developed the optimization software like this. When the polyhedral shape was concaved and convex in a random way, not really random, it is controlled, but looks like random. Some shapes are strong, some shapes will show weakness. So we have to control those geometries. And here we can see the simple sample model, or simplified so much. On the left, this is the model, or structural analysis model for the building itself. It is a little complicated, so this simplified one might be good for the demonstration. And I will show you the automated one later, but you can see the diagram on the right. There's some red elements you can see. It is showing too weak. So we should find the model without red element. We can move the node one by one. I have coded the program like that. And we can find with moving the nodes to have the model or without red elements. And it is checking the strength against the several load scenarios, such as only gravity or gravity plus seismic load in X direction or Y direction, or sometimes wind load for X direction and or Y direction, or sometimes snow. And in this diagram, it is showing safety ratio against material strength. But sometimes it can be buckling phenomenon, or sometimes energy absorption based on the vibration of the earthquake. And This method is applicable for some other shapes. This is also a polyhedral shape with down with the with So Fujimoto in Naoshima. And finally, we could realize this mesh structure, really transparent structure. And free form might be the really a typical way of optimization, using optimization, form optimization. And this is also the project with Jun Ishigami, the cloud arch in Sydney. We have done the design phase, so waiting for starting construction for this project. It has this ribbon-like structure, and the parameter for optimization is how this tower could be winded into air. This curve can be, the curved line can be optimized, and also the twisting angle can be optimized. So there are, we used 2 parameters of geometry for optimization. And it can be done by the software developed in my lab in the office. But in these days, we have a lot of 3D modeling software like rhinoceros and grasshopper or some other rabbit or some other software. So we can create the component of the software. For example, composing the software with rhinoceros, grasshopper, and my software. It is called Hogan. If it could be linked, the geometrical manipulation can be done by 3-dimensional modeling software, like grasshopper. And when the safety ratio can be checked by my software, this software component trying to check the safety ratio every time you change the shape again and again. This iteration is understood as optimization process. And other shapes like stacking shapes or multi-level or slabs structure can be is applicable for this method. And I can show you the automated one for the polyhedral shape. Just a moment. This is a software developing in my office. This is also the simple one. And I think many of you know how the optimization could be done. And so this is not so unique one, but if it is automated, at first the safety ratio shows 1.53. So over 1.0, that means too weak. And starting in the optimization like this, it is searching how the form should be transformed. And oh, it is it doesn't work, but I guess it is taking time. And it doesn't show how it is searching, but Oh, sorry, I couldn't show you how it is searching, but this is the final shape. The safety ratio shows the 0.699. That means safe enough, so we can build this shape. This is how the automated optimization works. And in this soft algorithm, I'm using the conjugate gradient method. There's a gradient descent method, basic one for the optimization, and a little, how to say, developed to find the answer, find the result faster, the conjugate gradient method we have. And some other methods are developed to find the result, find the solution quickly. And deep learning is, I think some of you have interest in deep learning. And deep learning is coded with this algorithm, gradient descent. This is not so much the topic today, but form optimization is optimization of input value. Such as coordinates X, Y, Z, or something, some others. That means when we had the formula like this, and coefficient alpha and beta is known, and we have to adjust X and Y. That is input data should be adjusted. And when the target S should be 1.0, we can adjust the X and Y input data to be adjusted. In other hand, the deep learning is the optimization of coefficients. That means that when we know the 0.1 for X, 0.5 for Y, results in S to be 0.1. Or some samples we know, or some conditions, combinations are known. Under that condition, coefficients alpha and beta should be adjusted. This is what deep learning is doing. So you can see the form optimization and deep learning is trying the similar method. So the similar algorithm is applicable for these. Also, I don't have so much time, but it is, if you have interest in these program, I think it is better for you to try coding. That is, for example, when I coded the conjugate gradient method like this, it is just 3 pages with C language like this, and the pages are when I print it like this, these 3 pages are showing the conjugate and the algorithm of conjugate gradient method. And in here, something we have to calculate for example, this code, in this code, the calculation, I mean, something function is only one formula, but it can be sometimes the safety ratio calculation of my software, and my software is the code, programming code of my software is a lot. So that program should be embedded here or here. So in that sense, the program is so long. But to make the conjugate gradient method, it doesn't take so much coding. You can see. And this is simple deep learning code. It is just 8 pages like this with this density of pages. 8 pages are not so many, so you can read it and you can code it by yourself. And I recommend you, if you have interest in this method, I recommend you to code without using libraries, something script libraries, you know, but it is better to code without them. And finally, you can have some original software, it will be better to try to develop more. And in these years, I have interest in local optimization. That is making dimple onto thin sheet or grooves or wrinkles like this. The arch is the one of the optimized shape, global with global optimization against the gravity. But when we give the wrinkles onto it, it comes stronger. And so that means the wrinkles or dimples are understood as local or optimization of shape. And 2 years ago, my student in master's course have found the flower dimples are stronger, much stronger than circle dimples or crescent dimples. So we are trying to scatter the flower dimples like this onto stressful area. And finally, we will be able to develop something free-form dome with scattered flower dimples or metal or thin metal or metal shell structure with these jasmine dimples. And they were using, because these dimples are applicable for thin metal structure, I have started developing the lunar Mars base with JAXA, that's Japanese NASA. It is a little confidential, but using those dimples and something deployable or structure for that. And energy absorption based on the seismic vibration will be applicable for the optimization, but I'll skip it. I think I don't have so much time. And for the buckling phenomenon, it is good to look at the eigenvalue equation. I hope some of you are a structural engineering student, but I'm not sure. But if you have interest in buckling phenomenon, it will be good to focus like this. All right, I'll skip it. And standard glass structure is developed in my lab as well. In my lab, some glass structures are developed like this. And extreme nature with Junya Ishigami is developed. In this structure, it looks simple as well, but the deformation and the bending stress could be reduced in this way. It takes time to explain this process, but using heat cambering, heating process, that we could give camber to the beam, to the roof, and the optimization software of the location of columns could be optimized with this software as well. And finally, the columns could become 60 millimeter or 32 millimeter like this. And I don't have so much time, but for the geometry, we can think some projects. I can show you some projects. Sunny Hills in Aoyama in Tokyo, with Kengo Kuma, is composed with timber structure. It is called kigumi in Japanese. Kigumi is timber joinery without using metal fixing. And for this structure, I have referred to Chidori or Jigoku grid, developed by traditional carpenters in Hida district in Japan. It looks like a perfectly interlocked upper, lower, but it is not easy to interlock more than 3 timbers perfectly going up and down, but these carpenters made it feasible like this. And when I was discussing, when I talked with Kengo Kuma, the meeting with Kengo Kuma is really a brief moment. It is, for example, it is around 10 minutes. He's so busy, I can talk with him only 10 minutes every time, and I have to develop something, some imagination from his few words, such as how about scattering lots of particles, and I could develop this kigumi timber joinery structure. This structure has the geometrical unit like this. Timber is continuous, but geometrically, it is understood as unit. And so it is kind of voxel system. We can stack this geometrical unit and create random shapes like this and select one as an optimized shape. And that can be thought as a random operation. And we can think of feedback operation. For example, we can know the volumes of structural element like this. For example, bottom of the columns should be thick, and around the corner of the top should be thick. So we can know the outline. When we could know the outline of the structure, it is easy to figure out how the elements should be assembled. That means the feedback is easy. And finally, we can optimize the outline of the shape like this based on the stress. Stressful area should be thick. And the pattern of Kigumi is constant, but because of thickness of the volume of the outline, we can see some random lights comes through this structure and makes komorebi or some other natural or light condition. And for the natural condition or komorebi space, I have developed a two-dimensional spectrum analysis. Single dimension spectrum analysis is like this, but I will skip it. And two-dimensional one is like this. For these photos, we can interpret this komorebi photo into two-dimensional spectrum like this. It is basically the three-dimensional graph like this, and looking at this three-dimensional graph from the top, we can find we can see this the pattern of a spectrum like this. And what we should do is draw the two-dimensional spectrum for some photos like this. These photos and spectra are understood as catalog of the spectra. And we can compare the structure we have developed or the spectrum, specific spectrum can be the target of the pattern of the structure. For example, this glass structure could have the spectrum like this, and you can see it is really similar to komorebi spectrum on the center here, right? And this is something cloud-like structure made of steel wire and washi paper, covered with washi paper. It had really similar to a fleecy cloud, the similar spectrum as fleecy cloud here. And Sunny Hills had this spectrum. It looks like the combination of something, the pampas grass field and fleecy cloud. That means we can explain which kind of naturalness these structures have. Something vocabulary we could use the spectrum as. And using only circles, we can make the spectrum close to the komorebi or some other natural scene. And so, because when we try to make a natural pattern, we have to have the technique to compose the elements in a natural way or random way. This is the one of the way of Kigumi structure developed more. I'm now in this library. This is three-dimensional diagonal Kigumi joinery. This is a library in Yusuhara town, done by Kengo Kuma. And for this structure, I have developed this timber joinery. The 4 timbers can be interlocked, and the center line can be crossed just at one point. And so we can develop the diamond grid like this, and the spacing, even if the angles are same, to make the constructions easy, we can think of spacing to be random like this. And so this geometry has not so many parameters, but finally it could show something naturalness. So we can see, I'm not sure it is natural or not, but and we had to reduce the number of timbers for the budget. But still, I think it still has some naturalness because of this randomness of the geometry. And when we could think of this, the structure to be composed with many elements, or we could have enough depth, like this roof or floor, the elements can become really thin and lightweight. So it comes safe structure, even if it collapsed. The people inside here will not die under that disaster. And we're developing, with Gengokuma, we're developing the more complicated kigumi shape. This is the pergola in the bottom of Carved Tower in Vancouver. Carved Tower is the skyscraper. Now, I'm not sure the constructions had started or not. But after that, at the bottom, this pergola will be built. This is just a partial model. It will have 40 meters long, 15 meters tall. For this geometry, I had to develop the flexible angle interlocking joinery like this. When it was interlocked, it looks simple in this the photo on the left, but we have to carve it like this on the right, and it cannot be carved by CNC right now. Also, we should develop. We should carve it roughly by CNC, and after that, carpenter's gonna finish. But we could develop the CNC a little more. I think it will become easier to provide a lot of this joinery, and it will come much more feasible to realize this kigumi structure or other or more complicated kigumi structure. And this is one of the computational design or parametric design could be realized. This is a really small project of treehouse in Setagaya. And for this project, around 400 panels of timber or wood could be assembled. And this is these panels are the main structure of this treehouse. It has this shape and interlocked like this. The 4 panels are overlapped at here. But when we could carve like this, it is possible to assemble in this way. And because the overall shape of this egg, this tree house has an asymmetric egg shape, such as looks like mantis egg. So we had to generate the panel or shape of each panel, or in this way, this is kind of parametric geometry. The tornado lines are crossing like this. Pink and purple lines are crossing like this. And from these angles, the interlocking shape should be adjusted. And finally, all the panels are generated, shapes of all the panels are generated like this. And we could check with this 3D printed model. And finally, the timbers could be carved by CNC and carpenters, like this, like this. So I could feel these computational design or parametric design are coming much more feasible in these years using these digital fabrication. I could feel when the digital fabrication technology it could be developed more. That doesn't mean the CNC will be replaced by the carpenters. Rather, we can try to extract more technique of carpenters. Carpenters have more technique to carve. So CNC could, when CNC could develop more, the carpenters can show more technique to carve. So we can develop the parametric design or those designs in parallel with the technologies, using those techniques parallelly. And for the using digital fabrication, I'm now developing this facade system with a Thai company and the Japanese company, Thai company Kinsey and Japanese company Heartland Engineering. It has this, the module has this shape, 4-branched shape, and each of them can work as a vegetation part and connected with cables. So it is it results in a tensegrity structure, and it could be the one module could be built as a mock-up in full scale. The mold could be 3D printed, and the stainless steel could be casted in it, and we could make this module. And if the 4 points of the module could be shared, the shape of module, overall shape of module can be flexible under the condition of 4 nodes and strength. Of course, it should have a specific strength, but we can design the module like this. And some other structures I'm focusing is a lattice structure, lattice structure like this. It is, for example, Eiffel Tower is lattice structure. You can see the element of lattice here on the leg of the Eiffel Tower. Each element, like this X element, or the flange element are composed with lattice again. So that means lattice structure. And right now, we can try to develop it into lattice structure. Using laser cutting and craftsman's welding technique. And so in some projects, I'm now proposing this lattice structure. Sometimes we should simplify it because of budget and time. Sometimes lattice structure on the flange and lattice structure on the web, or lattice plus lattice. Anyway, some projects are going on, and they will show the phase of feasibility where we are now. And the geometry of fuzzy node algorithm is developed as well. This is inverted question mark cube, and named by the students in Nihon University. And the structure is composed with just cubes. And the cubes are connected with each node like this. So we can understand this geometry using only the length of 1 or √2 or √3 of the cube. One edge can be 1. And here you can see the point node to node could be √2 on the surface. And across the cube, we can find √3 length. But it is not. It doesn't look like this shape. It doesn't look like the composed of only those 3 lengths. That means we can find the node to be fuzzy because of this joinery. It is connected by question mark screw called a heaton, and it has a little flexibility. So when we think of putting one more unit here, it is not easy. It looks not easy to put one more to here because the length doesn't look like one of those 3 lengths, but it was it was somehow easy to attach one more one by one on this in this workshop. That is, the fuzzy node is working well for this. If it was fuzzy, we can attach the unit easily. Easily. And this fuzzy node can be, we can see this fuzzy node system in this project as well. This is transparent structure workshop in Stanford University. We have developed the glass structure like this. And this pattern could show the Komorebi spectrum as shown as I shown previously. It is composed of really thin glass, 1.3 millimeter super tempered glass. It is called Leoflex or German Trail, or developed by AGC, the glass company in Japan. It is similar to Gorilla Glass developed in the United States. And using this thin glass, we have to control buckling strength or optimize the overall shape. And finally, the students could develop these shapes. And this is in Stanford University. And similar workshop I have run in Tokyo and developed, students could develop like this shape. Anyway, because of the fastener made of aluminum strap, we could bend it or twist it to adjust to the holes. So because of this joinery, the node could be fuzzy, and it was easy to attach the units, modules, one by one, like this. So if we could manipulate this geometry on display of the laptop, we can design the pattern, but we have to solve to create that tool, or we have to solve mathematically this fuzzy node. It is not perfectly solved yet, but some students in my lab have tried to put a little more conditions to solve the formula, or we are now trying the singular or eigenvalue analysis for this geometry. And the student, one of the students could develop the software to design the pattern like this. And this is almost final. Using spectrum method and optimization method, this is one of the sample we can develop. This is Komorebi workshop in Harvard, GSD, using PETG sheets trimmed out into this triangle or shape. We called it snowflakes. And these snowflakes are interlocked and inserted and assembled in this way. It looks like something shaved ice or something liquid or shaggy form. And it has a transparent form like this, and reflecting the lights in this way. We had to find the algorithm to convert this complicated shape into the structural analysis model. So we developed that algorithm, and finally the grasshopper, manipulating the geometry by grasshopper, and my Hogan software could be linked, and the shape could be optimized. And this is just a sample, or using Excel. Excel is also not only a grasshopper. The Excel is a simple software, but it also works as the optimization software. And the students could develop the Komorebi spectrum with these snowflakes. It doesn't have to be really a snowflake. It can be freeform like this. And you can see this Komorebi spectrum similar with this spectrum the students has developed. And these are final shapes. And the lightweight and ductile structures can be developed in this way. This is a structural design studio I'm running every year in the fall semester. Using this is done 2 years ago. using world thinnest fabrics called super organza and carbon rods like this. And the last year, with the school in Paris, ENSA, Paris Val de Seine, we could develop the 10-meter tower using the world thinnest washi paper and 3-millimeter timbers. And before this, using the same material, or this installation could be built in an insect exhibition held in Roppongi in Japan, 2-1-1 Design Site Museum. What it could be done with SciArc Tokyo Studio. Around 15 students from SciArc was staying in Tokyo for several months, so we could collaborate. And using thinnest washi paper like this and 3-millimeter timbers, we could develop 9 meters long, referring to caddisfly's nest. It can be understood kind of biomimetics, and because the washi paper can squeeze the frame, the timbers are working with active bending. And because of this active bending, the module can work as hard element. And overall shape was again developed by form optimization. And the washi paper could be dyed, plant dyed by the dyeing artist Chikako Sato, and the connection and the module shapes were developed. 54 modules were developed by SciArc students in the University of Tokyo students. And it was categorized, those were categorized by topological method to create as many patterns of geometry as possible. All right. These lightweight and so the lightweight and ductile structure will prevent death in the event of a collapse. So these workshops are not only the opportunity to learn for students. In these workshops, we are developing the structure to prevent death of people. And so when we finally, when we think of natural space, we can think of saving people at the same time. That's our thoughts for engineers. All right, that's, sorry, it took time. That's all for today. Thank you so much.
Thank you very much. Geez, the depth, the breadth, the range of the work is just, it's overwhelming and exceptional. And I mean, I really look forward to you coming to USC at some point in the future to conduct one of these workshops. Mm-hmm. So I think we have probably 10, 15 minutes to take some questions. Mm-hmm. And, oh yeah. Camera, and Takako can, I don't know if she's hearing me. Maybe give me a hand with the questions. It usually takes a couple of minutes for them. To post, but while we're waiting, Jun, I have a question maybe that you can elaborate on a bit. You know, having some sense on the whole idea of the laboratory and the university, which is a bit different from what we typically have here in the United States. I'm interested if you can just expand or expound a bit on the relationship between the work you do with your students and the research and questions that you pose with the work that you're doing in the professional environment.
The projects in my office, I mean, professional engineering projects we have, is I think you can imagine how it works in the office. We're collaborating with architects and developing the structural design. And when we develop the structural design in that way, sometimes I find some ideas to develop, but not applicable in a specific project going on. Because of mostly because of time. So those ideas can be developed in my lab. For example, the spectrum method to analyze or optimize the light condition, optic condition, or creating natural space. It takes time. It takes a little more process to develop. So that kind of topics can be experimented in my lab. Mm-hmm. And there are some practical projects in my lab as well. And for example, we're now developing the facade system I showed using stainless steel casting. That is something structural system we're developing. And the lattice structure is also developed in my lab. And I'm thinking, I'm proposing in some competition or some projects, practical projects in my office, if we can adopt those facade structure or tensegrity structure or lattice structure or some natural space. Fuzzy node geometry to create natural space like that. So those are the relationship between lab and office.
So we have some questions coming in, which Takako, maybe you can pick one. I just so I won't ask a follow-up question, but I'll just say that it sounds like the boundaries are a bit more blurred than maybe what we're used to, and quite productive in part. I mean, when I did the introduction, I made reference to the role and importance of experimentation and research, and it's just it's great. I mean, I got the sense when we were at the university in Tokyo of this, but it's you know, seeing the elaboration in this lecture, I have to say, is just really great. You know, that the student labs and the work of that caliber and innovation is occurring at that level. So let's, Takako, can we take a question? I see Yo and Scott.
Yes, so maybe we'll start with the more sort of general or overarching question rather than like the specific questions related to the structure. So we'll start with this one. You speak a lot about optimization, but in reality, is it truly about optimization I think that's a very humble way of framing your work. It is obvious that people don't just go to you for the software, but perhaps like Jörg Schliach, there is an emphasis on efficiency along with an artistic quality. Is there an agenda in your artistry?
When I say optimization, the optimization should be always in any projects, every project, we're trying the optimization. That means even if it was simple or project, when the column was too weak, we should think how or to be strengthened it. If it could be thick, or we can put one more column like that. That is kind of optimization. So the idea of that simple way could be developed more and more and more to become the method called form of optimization. So there are some phases for the optimization, that kind of simple way or complicated way, and using software or developing software is some students have I guess some of students have interest in developing the software or code the program, simple program. No, I'm not sure simple or not. But anyway, it is good to have the original tool or to develop your own method. But it is not always necessary, I should mention. But if you have had interest in developing your own software, I think it is really helpful and useful. So little by little, we can develop that. So it is good to start coding the software. I'm not sure. This is a topic of your question or not. But, the optimization is really now there is lots of topics in the optimization field.
Okay, let's take another one. Takako?
Is that okay, Takako?
Yes, I think so. I mean, I guess like maybe also related to that question, I mean, there's probably some questions about like the, collaborative nature of your work, right? Mm-hmm. How it's not done solely, on your own, but rather it's probably through a series of feedback and back and forth. So, but let's get to this one question about Kigumi. So there's a question or a series, maybe it's a couple of questions. Kigumi is a ductile resilient system. Can local optimization also create reliant systems in what might be technically rigid? And then a follow-up to that is, can Kigumi systems lead to potentially kinetic structures?
Yeah. first of all, the Kigumi structure is, especially I'm developing the Kigumi structure with small timbers, thin timbers. So it comes up to composition of the lots of elements. And for timber structure, there's a term, oh, what was that? Sorry. Oh, I'm sorry. I forgot the term. But one of the term is kind of load sharing or load distribution. That means the hard timber, the timbers have the difference, some differences of the hardness and strength. Even when we use the same cedar or cypress or other woods, even if we, for example, when we use cedar in Japan a lot, but the cedar timbers have the difference little by little, or that is tolerance. And hard one has has more strength, and soft one has more is weak. That means weak one doesn't share more loads because it is soft. So finally, the hardness, because of hardness and strength, are almost proportional. Or we don't have to take care of the relationship, how to say, weakness of the weak timber so much. It is a little hard to explain, but finally, the Kigumi structure with many elements has the sort of ductile and resilient system. And the focusing to that point, I think the local optimization can be developed in that way, because when we had to think of ductile or resilient system, we need ultimate state analysis of the structure and detailed model or detailed sample model. But when we could survey that kind of model, and we could have, if we could have the algorithm to simplify that model, or the optimization algorithm can be applicable. So yeah, in that way, it comes. It will be possible to apply. The optimization method will be possible to apply in that way. Right. And for the kinetic structure, of course, the Kigumi system, Kigumi system is really suitable for kinetic structure. Of course, it should have some how to say spacing for the motion, but I think some how to say mechanism will be applicable. Or for example, with Kengokuma, I have developed the XYZ grid system using Kigumi. But when we assemble that, when we assemble that Kigumi, we should turn finally the one timber to complete. That means this has the flexibility for the twisting motion. So like that, Kigumi can have something kinetic mechanism. So I think that's a good idea to apply for that kind of structure.
So we still have a bunch of questions, but I think we're being told that we have just time for one more question, and I think I'm gonna maybe.
Sorry for taking time.
Oh no, it's not. It's totally fine. But there's this one question that I think is probably something that maybe a lot of students would be interested in, and it's this one. A number of your projects involve complex sculpture-like geometries that would be impossible to complete without advanced structural knowledge. How much of the original design by the architect has been adjusted for structural integrity?
In these days, the structural performance or something knowledge for the structure has increased a lot. So I think the architects don't have to know all of them, of course, and sometimes we structural engineer propose the geometry itself because we engineers are good at mathematics and dynamics, and I'm not sure, and some architects are good at it, and some architects are not. but with each architect, we can discuss those geometries and dynamics, and even the geometry, it might be better if the architects could manipulate the geometry, but I think I can propose some geometries like I showed, for example, fuzzy node, or something some geometries for Kigumi structure, like egg-shaped treehouse, or those. Basic idea, basic sketch can be provided by architects, but applying the mathematics or geometry for that can be done by us sometimes. So those development of geometry and dynamics, and finally the structural design can be generated from the discussion. Especially sometimes I have some ideas for the structural design, and I sometimes propose architects, how about using this structural design, or how about using this structural design? I already have. The ideas I already have. But the architects, in many cases, architects don't select that. Rather, from the discussion, when the architects prefer to develop the structures from the discussion, not using the ready-made structural design. Yeah, so that's how how I develop those designs.
Okay, I think we will conclude there. And once again, on behalf of the dean, our students, the staff, the School of Architecture, we want to thank you for your time and the lecture.